Right, in this problem, we've got the astronaut in his spacesuit, and he is 300 meters away from his spaceship, and he's moving toward it at a velocity of 10 meters per second, which he decides is too fast to slam into the spaceship and try and safely enter it. So he pokes a hole in his glove to give himself an acceleration of 0.1 meters per second squared. So we want to know, first of all, how long it takes him to reach the spaceship, and then how fast he's going when he gets there. So let's, first of all, we have to decide our direction that's positive, so we'll call our positive direction to the right. And then we need to take all of this information and try and translate it into kinematic variables. Okay, so we're told that he's 300 meters away from the spaceship, and the way that I've drawn it, the spaceship is to his right. So we might as well call his initial position x naught equals 0. And that would mean that the final position, or the position of the spaceship, is 300 meters. Now, what does it mean for him to reach the spaceship? It means his position is going to be the same as that of the spaceship. Okay, so that's our final position. Now, what's his initial velocity? We're told that his initial velocity is 10 meters per second. All right, so we put that there. What's his final velocity? We actually don't know, and for this first part of the problem, we may not care about it. Okay, we can't assume that his final velocity is 0. That would be nice. I mean, if he reached his spaceship right as his final velocity reached 0, then he could just lightly grab on to the door frame, and everything would be perfect. But we can't assume that. Okay, now we call the starting time t equals 0, and then the time when he reaches the spaceship, we don't know that, and that's our target variable for the first part. Right? It asks us how long it takes him to get there. Now we're told that the acceleration is 0.10 meters per second squared. Now when you're given these quantities in the problem, you're usually going to be given the magnitude, and you have to figure out from the problem whether that should be a positive or negative value. So for instance, his initial velocity, well, he's moving toward the ship, right? So v naught is to the right, and if we look at our axis, which tells us which way is positive, v naught points to the right, that's a positive direction. Now if he's trying to slow down, that means that his acceleration is to the left. Right? So that means that we should write this down as a negative number. Again, so we're told the magnitude that that poking a hole in the hand of his spacesuit is going to give an acceleration with a magnitude 0.1 meters per second squared, but it depends on which way he points it. So if he pushes his hand forward, then the air that's coming out of his spacesuit is going to help slow him down. But if he pointed it the other way, it would speed him up, which defeats the purpose of what he's trying to do. Okay, so now we look at our kinematic equations. In our kinematic equations, first of all, we have the velocity equation. And during the discussion, a lot of you saw this equation and said, oh, it has time in it. It looks nice and simple. I just want to work with that. But you'll notice, if you start out by focusing the problem, you'll notice we don't know the final velocity. And we also don't know the time. So we got two things that we don't know, so we can't go ahead and work with this problem, or with this equation. We have to look at the position equation. And if we look at the position equation, we know everything in this equation other than the time. So that means that we can solve it. So, don't get, it's tempting to try and use this equation and say, I think a lot of people plugged in and said that the final velocity was 0, and you can calculate a time from that, but it's not the time that we're looking for. We're looking for the time that he reaches the spaceship. If you solve for the time when v equals 0, that's the amount of time it would take him to slow all the way to 0, which is a completely different question. Okay, so now we look at this equation and we say, well, we know the final position, we know the starting position, we know the initial velocity, and we know the acceleration, but we don't know time, right? And so that means that we can solve it. Now, just to make our lives a little bit easier, I'll cross out this initial velocity, say that's 0, or sorry, that initial position, we know that's 0. Now, looking at this equation, I've got a t and a t squared involved, and a term that does not involve t. So that means that we're going to have to use the quadratic formula. The only way to solve an equation like this is the quadratic formula. So the first step to doing this is to move that x to the other side and rearrange things so that the t squared is the first term, and then minus x. Okay, so this is just the way that mathematicians like to order things. They like to go from highest power to lowest power. And then that allows us to define, if we look at our quadratic formula, this is the a, this is our b, and this is our c for the quadratic formula. Okay, and I'm using capital letters here just so that we don't confuse the a for the quadratic formula with the acceleration. And so the quadratic formula tells us that the time is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. So that's negative v naught plus or minus the square root of v naught squared. So it's v naught squared minus 4 times our capital A, which is 1/2 the acceleration, times c, which is negative x. All right, so you got to be careful to keep all those keep track of all those minus signs, and then all divided, meaning both terms, by 2 times our capital A, which is 1/2 times the acceleration. Okay, so simplifying that slightly, we get negative v naught plus or minus the square root of v naught squared There's a minus times a minus, so that becomes a plus. 4 times a half is 2, so I get 2ax, all divided by acceleration. Okay, so that's kind of tricky to follow through with all the variables. Sometimes it's easier to just use numbers at that point. But in this case, I know that I'm going to be doing this problem, this is basically the same problem again, with a different acceleration, so I'll be able to use that same calculation again. Now, please feel free to use, I know some of you might have graphic calculators that will allow you to solve the quadratic formula using those, or use a site like Wolfram Alpha where you can just plug in your values. That's at least good as or if you just type in the equation with the equal sign, it should solve it for the time for you. Okay, so if I plug in my variables there, my known values, and make sure that I do everything correctly. Now the question is, should I use the plus or minus sign? If you think really hard, you might be able to figure out which one is sensible ahead of time, but I always just calculate both, right? So you got to do once with the plus sign, once with the minus sign. So I get t is equal to 36.8 seconds or 163 seconds. Now, the question is, which of these would be the one that makes sense? Well, if you think about what happens, he's going to approach the ship and still be moving to the right with a positive velocity at 36.8 seconds. So that's probably he's going to hit the ship at that point. But if somehow he missed it and kept accelerating, he would eventually pass the ship, turn around, and come back. And he would get back by the 163 seconds time. So both of those, the math can't tell you which of those makes sense. But if we think about the way that this would actually look, he's probably going to run into it the first time. So it would be the 36.8 seconds. Then the second question says, well, what's the velocity at that time? The velocity, now I can calculate because I can say v is equal to v naught plus acceleration times time. I know all those quantities now. So v naught was 10 meters per second. And then acceleration is negative 0.10 meters per second squared times the time, which is 36.8 seconds. So I calculate from that the velocity is going to be 6.4 meters per second. Now, a few of you, as you were working on this problem, I saw that you used a positive acceleration, so you got a different time. You got like 26 seconds because he actually sped up, and then you calculated that the velocity was 12 meters per second, and then you just kept going. Well, you should pause and say, does this make sense? Right? I got a velocity that's less than the starting velocity, and it says that he's in the problem that he's trying to slow down. So that's a sensible answer. If you got a number that was bigger than 12 meters per second, you should go back and say, hey, that doesn't make any sense. All right. Okay, so this is definitely a problem that you should be able to solve. So it was certainly set up to try and get you to make some mistakes, recognize those mistakes, and go back and work on those in the future. Now the follow-up problems, and this was partly just to give you some more practice and things to think about. In the second part of the problem, it says now he pokes a hole in both hands, so use an acceleration that has magnitude or absolute value 0.20 meters per second squared. Okay, and so again, he's trying to slow down, so that means because the velocity is positive, the acceleration has to be negative. If you take that and plug that into, it's going to be the same quadratic formula. If we use that there, it turns out that if you plug in those values that are given, within the square root, you're going to get a negative number in here. If you use Wolfram Alpha or something like that to try and solve that can deal with imaginary numbers, it's going to tell you that number is imaginary. If you certain calculators will just give you an error. But either way, imaginary time is not something that we can work with. Right? So time has to be a real value. So what that means is there's no solution. There's no time at which he reaches the spaceship. Okay, so no solution. He never gets there. The acceleration, the slowing down is too much. He slows to a stop and turns around before he ever gets there. So if we think graphically in part one, if we look at his position versus time, he's trying to get to something 300 meters away, but he's slowing down. So in part one, he takes a path that looks something like this, right? A parabola that intersects once at about 37 seconds and once at about 163 seconds, right? So we might say, well, this part doesn't make physical sense because he would have already gotten to the spaceship by then, so he never does that. But maybe he misses and comes back around, or turns around and comes back. In part two, if we make these graphs, what it would look like is position versus time. He's trying to get here. It looks like this, right? So he turns around too quickly, and he never gets there. Now, part three, we're looking for, and now this is a really challenging problem, and it's kind of just put in there in case anybody happens to solve really quickly. We're looking for the case where he gets there just as he's about to turn around, right? So the equation would look something like this, but we would know that when he gets to the spaceship exactly at that turnaround point, he's going to grab on. So since this is, so I wanted to definitely get to the part of looking at the plotting of the three different possible cases. But the algebra in this is a little bit trickier, so I'm going to leave that for a separate video, and the solutions are going to also be posted on Blackboard.
There comes a time when our dreams of the 21st century must be weighed against the realities of today.